Hello everyone, I'm Hosein. Today I'll present the power of neural network models to classify sleep stages from polysomnographic recordings using three approaches: baseline random forest, feed-forward neural network, and a transfer learning neural network. Here's our roadmap. First, I'll explain the problem, then we'll look at our data source and pre-processing steps. Next, I'll describe the baseline neural network, followed by the transfer learning architecture. Then we'll finish after comparing our results. We treat sleep staging as a multitask classification problem. From each 30-second epoch of extracted features, we predict 6 or 5 or 6 stages: wake and 1 and 2 and 3 REM, and movement class. For transfer learning, we drop the movement stage because it's too rare in our target data. We use the Sleep-EDF expanded dataset on PhysioNet, which has nearly 200 full-night recordings split into a sleep cassette, SC, with 7 channels and sleep telemetry, ST, with 5 channels. We trained each record to 30 minutes before sleep onset and 30 minutes after final awakening to focus on meaningful epochs. Here's a sample of an SC recording with exact time and frequency domain features so that raw signals feed into our classifiers as feature vectors rather than waveforms. Note that the sleep cassette data has 2 more channels measuring body temperature and the nasal airflow. From SC, we extracted 73 features per epoch, and from ST, 65 features. We normalized all features, saved them to CSV for faster loading, and split data 80 to 20 for training and test, holding out 20% of training as validation. Our baseline is a simple 3-layer feed-forward network with 256 and 96 and 48 neurons with leaky ReLU activations and dropout of 0.3, 0.1, and 0.4. These hyperparameters are the best choices after random search tuning process. This diagram shows our transfer learning approach. We train a 7-channel base model on the SC data, freeze its weight, and add a projection layer to map 5-channel ST inputs into the same feature space. We then fine-tune the head layer on the ST data. And here is the parameter summary of how the model look like. We add 2 dense layers at the end to retrain on the ST data. The SC base has about 41,000 frozen parameters after projection and 2 small dense layers. The trainable head has around 8,000 parameters. We fine-tune with Atom at 10 to the power of -5 for up to 300 epochs using early stopping with patients of 20 to avoid overfitting. Here are RAG curves for each class on the ST test set. You can see that both models achieve high separability, especially with the transfer model slightly better on each stages. Focusing on the stage N1, the random forest gets the F1 score to 0.45, the simple neural network was 0.51, and the transfer neural network F1 score was 0.56. Transfer learning thus improves detection of this underrepresented state. In summary, combined random forest achieves a very high accuracy with micro F1 0.83, and the combined neural network is slightly better in accuracy, but with a good jump in micro F1 score. Transfer neural network around 4% less accurate, but remains strong in micro F1 score. In the recent study of Gaik et al. 2022, which they have a complex architecture. They train on the full signals. And here are the key references. Thank you for your attention. Any questions are welcome.